Would you say you're more on the optimistic side of that argument then, in terms of actually finding?
I'm a scientist. I don't have the luxury of being optimistic.
You're listening to the Cosmic Cast.
Hello, and welcome to another episode of the Cosmic Cast. I'm joined by Ricky Bahir.
Hello.
Tom Harvey.
How you doing?
And this week we are joined by Alastair Tait from the University of Stirling. Hello.
Hello, everybody.
So, how did you get into microbiology, and how did you end up in Stirling, I guess is our first question for you.
Well, I'm a meteoriticist from Australia, so I was doing my undergrad and everything at Monash University down in Melbourne, and for a few years we were doing meteorite recovery from the Nullarbor Plain, because I always really like space, I like Mars, I like meteorites, and I originally had my PhD project was looking at the sulfur cycle of Mars, but I'd only really just started only doing it for a month, and then we went out to the field and we found meteorites, as you do, and then I had this idea that I found all lichens growing all over these meteorites, and I was like, I wonder what microbes like to eat them down. I know there was some microbes that like to eat sulfur, and I'm like, meteorites have sulfur. I wonder if they eat the sulfur, and then all of a sudden, that's how I went into being a microbiologist, essentially. So I had to learn that and do all those techniques. It was good fun.
Bugs eating rocks.
Yeah.
Cool. So how many times have you been out collecting meteorites there in Australia? Is that the main area where they do most of the collection?
That's where they do most of the collection of meteorites in Australia. The reason why is because it is a semi-arid desert. Mm-hmm. It's the largest limestone karst in the world, and it doesn't have any erosion or deposition of other sediments, so it's just flat, and it's always flat, and it's been flat for about 1 million years. Mm-hmm. So we go there and we find meteorites, and limestone is white and cream, and the thing about meteorites is they're brown and dark, so it's really a case of just spot the difference. So I've organised and been on these about 7 years now, and we found about a quarter, maybe even a third of Australia's meteorites.
Wow.
In about 10 years we've been doing it, but I've only been doing about 7. And we have such a backlog. Like, there's only my old PhD supervisor, 2 PhDs, no postdocs, and a couple of honours students, and that's about it. So
wow, that's a lot of work.
Yeah, and there's a lot to go into identifying a meteorite and classifying it up to the standard of the nomenclature committee. So, we only seem to identify the meteorites we need as we need them. So we have a backlog.
Fair enough. Mostly chondrites, I imagine.
Mostly chondrites. It's really funny. We haven't found any ions out there, though. So we found about, 300 odd meteorites now, 200-300 odd meteorites, and we haven't found a single ion.
Wow. Yeah.
So, which is a statistical anomaly. We found ones from Vesta. We found carbonaceous, but yes, mostly anuralites, which are good. They blunted our wire saw because they're full of nanodiamonds. But we found, mainly chondrites, but no ions. So we have some ideas of why that might be the case, but we need to test that.
We had Dr. Catherine Joy on, and she'd been to Antarctica to look for meteorites. They found that obviously you find less iron meteorites down there as well. Which in general on Earth, there's a lower population of iron meteorites than you would expect to find. But in Antarctica, it kind of makes sense because you've got all this ice and the snow, so you might get some kind of heating that causes them to sink into the snow. But I guess in Australia, that seems like...
We think there's a similar sort of thing going on.
Okay.
So the thing about the Nullarbor is that the ground elevation doesn't change by more than maybe a metre at most, but you still get sort of paleo lakes.
Right.
And when most of the surface is what we call a gibber surface, deflationary, so all the sand is blown away and you just leave pebbles and rocks or meteorites, that sand still has to go somewhere, and it usually falls into these lakes, and it periodically floods, like maybe once or twice a decade, and it's full of very, very fine muds and clays. So what we're thinking might be happening is these ions are landing on this really soft surface, and then eventually they get, when it's not there, the wind is blowing away all the sand, and that allows them to deflate a bit further. Then you have a flood and it just buries them. So we're thinking there's something similar might be going on with those there, but we have no idea. We need to test it. We need to find an iron first before we can prove that idea.
Yeah.
We talked to Katie a bit about some of the problems associated with looking for meteorites in Antarctica. Presumably in a desert is procedurally quite different, although I guess maybe not so much. It's hot instead of cold. What's the process for actually looking for them when you're actually on the ground basis?
Well, we have this little search technique. So there's a few old tracks that you find there. And what we do, there's about 5 or 6 of us, and we get out of the meteorite and we sort of make this flower petal shape. So we sort of go in these big, large circles and away from the... you remember those little things that you probably did in primary school where you got a pen in a shape and you made these sort of spirograph? There we go. So we sort of make spirograph shapes away from the car, because when a meteorite comes in, it breaks up and leaves a strewn field, and these can be anything from a couple kilometers to a couple tens of kilometers across. And if you're trying to find a meteorite, you want to spread out a lot to try and get these things, and you can cover quite a lot of ground. Whereas if you're just doing a line search, which is definitely the most efficient way, but you're only covering a very small amount of area. So you want to try and cover quite a lot of area. But you might have missing bits in between, but you increase the amount of chance that you'll intersect a strewn field that way. And we've found about 3 or 4 strewn fields now out there as well, which is really, really cool. When we go out there, we have a magnet stick. So we go around and most meteorites are magnetic. All the interesting ones are not, though. So you go up and we try and find meteorites. But if we recognize that it's a meteorite, we don't magnetize it, because it might destroy the paleomagnetism, and some people might want that. But we're going out with, undergrads and honors students, or maybe even other professional meteoriticists, but they haven't actually really looked at meteorites before, and so they need the magnet stick to probably find something. And rather than find something and it's been magnetized, rather than not find anything at all.
Exactly.
So,
For your research then, in terms of looking at the microbiology within these meteorites, have you got to be extra careful in terms of the curation and bringing these things home? I guess it adds an extra layer of complexity relative to just the normal chemistry people do.
Well, yeah. So yes. So for most of the stuff, I'm looking at microbes that are inside the meteorite. So stuff on the outside, I don't really care that much about. But if I am collecting samples which I know which are on the outside, then yes, I definitely have different collection protocols for doing that. When it was genetic stuff, we had to have very, very strict collection protocols. But if you're looking for stuff which is growing on the inside of cracks, you're not too bad. As long as you're not licking them or like whatever, you should be fine. It's just because what you're looking for is on the inside, so you can just hit it with a hammer, break open the side, and put it under a microscope, essentially.
When you're curating these samples, do you worry about changes in temperature in any way, and whether that will affect what microbes can exist within the samples or not?
Yeah, so we try to keep the meteorites as close to the ambient temperature as we can, because if you take a microbe out of the environment that it's used to, it will have some sort of environmental shock and die. Some things are frozen, but anything that I was using for microbial sort of stuff are essentially double bagged, sitting in an ambient temperature in Melbourne. Now, ambient temperature in Melbourne is completely different from ambient temperature in the middle of the Australian desert, as you can imagine, but you got to do what you got to do. There's only so much you can do for these sort of things.
So extrapolating from this, the end goal really is to apply some of the techniques that we will go on to talk about with you to meteorites we get from other planets, but on the surface of those planets themselves. So specifically Mars is the closest example at the moment to that. So when we're getting samples from another planet like Mars and we're having to take it back, are we not worried about whether there's going to be these temperature changes, or how difficult it's going to be to curate these things as they're being taken back? Last
year, there was a report by IMOST, which is a bunch of scientists looking at curation and collection of all sorts of rocks, really. In fact, they didn't really focus on meteorites, but they just focused on collection of all sorts of rocks from Mars. And these are very important questions. So they have a whole bunch of requirements that these rocks are kept within certain temperature profiles, certain temperature ranges, certain pressures, certain radiation environments, and things like that. They're trying to keep them all within certain variations to get them back home, because obviously it's going to be quite an exotic journey to go from the surface of Mars, been put in a tube, put onto a rocket, blasted into Martian orbit, collected by a European thing, fly through space, which is double the amount of radiation that it normally gets, come through fiery stuff, and smack bang back into the desert somewhere in America. Now, the crazy bit is that because it's coming back from Mars, it's just coming back in a heat shield. There's no parachute or anything, so it's going to slam into the desert at few hundred kilometers per hour. So it's going to be quite the delivery, essentially. So that's all these things could potentially change the chemistry or potential biosignatures or life if it's there. I don't think it'll be there, but if it is there, luck, it's going to be not having a good day.
Yeah.
That's for sure.
So you say that you don't think there'll be life there now, but I guess a rather needed element to your research is that there was previously life.
Yes. So I think the chances of life on the surface today are very, very slim. I think the chances of life in the past are, pretty good. Like it's at the moment where the more we learn about Mars, it looks very similar to early Earth, maybe a bit cooler, had a bit of ice, but, it's still pretty interesting. There was a lot of fresh water around, and there was a lot of potential energy sources. So it's a case of the lights are on, but no one's home. Yeah. So could have been life. We don't know. But I think when we start getting these samples in and we know where they're from, we should be able to potentially answer this question in the next 10 years or 15 years.
Would you say you're more on the optimistic side of that argument then, in terms of actually finding?
I'm a scientist. I don't have the luxury of being optimistic. I think it's well worth a look. I think is the thing. I'd like there to be. Yeah. But what I like and what there is are obviously two different things. Yeah. I think it's definitely worth a look.
Yeah. I guess this hinges on finding a meteorite then that is then collected from the surface of Mars.
Yeah, so my research is not looking at other so just normal rocks on Mars, but meteorites on Mars. So the reason why that I care about meteorites on Mars is because meteorites themselves, we know a lot about them, right? If I pick up a Martian rock and I'm trying to find a biosignature in it, we don't know if that signature we're looking at is just a quirk of Martian geology, starting composition, how many alteration histories it has. There really is not much really we know about that. And that's the reason why we're going there. We wanted to learn about these things. Yeah. So that's not necessarily a bad thing. But if you have, say, a sample that most things about it already, like a meteorite sitting on Mars, then it becomes a witness plate. It's like a standard. It falls in a meteorite, very poor secret, and I'm going to make a lot of planetary scientists cry here, but, most meteorites are the same. They're, we kind of know what they are. They've got very narrow isotope ratios, very narrow mineralogical isotopes. We know their formational histories, know when they formed. There's a lot of things we know about them. So if you then push that out of those ways, because when they come into an environment, they're out of chemical equilibrium. They're going to start reacting and creating alteration products. Now, most meteoritists hate alteration products because they're always trying to get to the primitive, the pre-solar, the great sort of stuff. Whereas me, I'm interested in this weathering stuff because that weathering stuff records stuff about the environment, the temperature at which these minerals formed, what was the pH of these minerals formed, what sort of atmospheric changes, salinity, all those sort of information, abiotic environmental things, which is the stuff we want to learn about Mars, right? Because it tells us about habitability. But the other thing is, if there's life there, life has a way of, especially when it comes to isotopes, likes pushing isotopic values in different ways than, say, normal temperature would. So you could potentially record a biotic signature if it was sitting at the surface. And because you're doing it to a sample that you already know what the starting value is, such as a meteorite, you have a much, much better way of looking at that sample than if it was, say, just a Martian rock, which you pick up and you don't know.
Could be anything. Is there a particular type of meteorite that's best to try and identify this signature?
Yeah, so I think the best thing to look for would be a chondritic meteorite, specifically an ordinary chondrite. Now, the reason why on Earth they make up something like 89% of meteorites that we find on Earth, but on Mars we've only found 3. Now, some people might find this quite interesting, but we've actually found meteorites on Mars. In fact, the rovers have found 45 meteorites, but the vast majority of those are iron, and as we've already discussed today,
the opposite of Earth.
It's the opposite of Earth, right? But the reason is that meteorites, when they weather, they look brown, and the thing about Mars is it's brown. And these rovers, they're going to Mars and looking for Mars, and they're really caring about bedrock because that's in situ, and you can tell something about their scrappy little surface rocks you don't really care about that much. And the way meteorites break down is that an iron meteorite stays iron, and it's this big thing, whereas an ordinary chondrite gets smaller and smaller and breaks up, and it becomes very hard to spot.
Yeah, so it's very much an observational bias. Then, I guess.
Yes,
Yeah.
but if you can find an ordinary chondrite and it's small enough to fit in one of those tubes, or large enough that you can drill it without, dislodging it and creating problems for the rover, if there's engineering things, I think it could create quite a lot of value, not just from the long shot of trying to find a biosignature, but the fact that because it records all these environmental factors, all these environmental weathering things, it can provide potentially value to other samples that you're bringing back. So you could remove overprints from later alteration events, which may only be recorded in the meteorite. So then you can start to decipher some of the regional geological information.
So I guess some of the sample return missions like ExoMars have started to think about site selection, and they've selected a site now, I think, haven't they? Is that location quite reasonable to be able to expect to find meteorites there, or?
Well, the thing we know about from meteorites on Earth is that a meteorite is roughly the same percentage across the planet for finding a meteorite. You get about 10% less at the poles, but for all intents and purposes, what we know, it's about the same across the planet. We shouldn't expect those sort of ratios. Now, Mars is potentially a really old surface. So on one hand, there's no crustal recycling on Mars, right? So there's no plate tectonics. So the surface there is potentially billions of years old. And they've done some cosmogenic dating using Curiosity rover to have a look at how old sort of the modern erosional sort of things are going on. And that itself is like 73 million years old or something like that. So really, really, really old surfaces, even by Earth's standards. Now, the Nullarbor is about 1 million years old at most. But there's been climate change through that time and, obliquity changes. So you may be looking about maybe 20 or 30,000 year old surfaces at most. So what we find is that when we go out looking for meteorites there, 1 year into 2014, one person walked 135 kilometers and found 14 meteorites. The short one, which was me, I trundled 90 kilometers and I found 6 meteorites. And this translates to you would have to travel between 9 and 15 kilometers before you found a meteorite. So imagine going for a hike, and then and if you hike between 9 and 20 k's a day, you'd find about 1 meteorite, which is kind of what we find on average per person. Now, to put things into perspective, the rover Spirit trundled 7.7 kilometers in its life and found 3 meteorites. Opportunity did 45 kilometers and found 16 meteorites. This is about 2.5 kilometers per meteorite find. So already about 4 or 5 times better than what we are. But the real winner at the moment is Curiosity, which it's done 22 kilometers and found 27 meteorites, which means it doesn't even need to do 800 meters on average before it finds its first meteorite. So the difference is between here, which is something which is really good to keep in mind, is that we went to the Nullarbor specifically to find meteorites, whereas the rovers are there to look for Mars and bedrock. They're not even really looking for meteorites. They're just stumbling across them and go, oh, there's a meteorite, I guess we'll analyze it. So and it's also looking through camera lenses, and it's kind of looking down a pipe essentially. So I'll put it in perspective that if they were actively looking for them, they had a geologist there with a magnet stick and running around, it would be even higher still. So Mars is definitely a meteorite graveyard. Yeah.
I wonder whether you'd find a similar thing with the moon then, because of a very ancient surface that it has. I assume you'd probably, if we could, find lots of meteorites there as well. It'd be interesting if we ever send a sample return there to look for them.
Funny enough you asked that. We actually have that answer. Is that I think it was Apollo 14 or Apollo 12. I can't remember which. But they just picked up some regolith and brought it back, and they found 2 chondrules that were partially melted in the surface. So the trouble is with the moon is that there's no atmosphere, so they don't get slowed down, and they just impact and shatter. They travel kilometers per second, and that's the end of the meteorite. It's in 1 million small pieces. But they have found fragments of meteorites in the moon, and these were samples of accident. And I think that's what we're going to probably find when we bring samples back from Mars, is the fact that these rovers are probably going to drill down, and they're going to drill into rock, which is roughly around about the same age as the late heavy bombardment, give or take, and that's when the flux rates were much, much, much higher than they are today. Like when most people think about meteorites, like they're like, oh, what's the chance of finding a meteorite? That doesn't sound very much. I haven't ever found a meteorite. And it's like, yeah, because you're not in the Archean, right? It's like this was a much more common geological phenomena billions of years ago than it is today. So I think, and that's the sort of rocks that we'll be sampling from. So I think the chances of finding chondritic fragments on Mars is going to be incredibly high in the samples that returned.
That's pretty exciting then, really.
Oh, yeah. And apart from learning about the environment as well, apart from learning about potential biosignatures, is that there's these things called extraterrestrial chromites, and we find them all on Earth. And they're I guess you could say the last part of a meteorite that weathers away, and they get weathered out and they just float around. They're very hardy. And what you can do, you can zap these, and you can look at their isotopes, and they record the signature or the parent body that they came from. Wow. So one thing we found out is back in the Ordovician, there was this massive disruption event somewhere in the asteroid belt, and then we all of a sudden had all these L chondrites coming to Earth, and that's the reason why now most chondrites that we find now on Earth are L chondrites. But you go back prior to that, most meteorites were A chondrites. Chondrites were actually in the record prior to the Ordovician breakup quite rare. So by going back to these rocks on Mars and potentially looking at fragments from these things, we might be able to determine meteorites that were falling to planetary bodies 3 and a bit billion years ago that might not even be in our collections on Earth. Yeah.
So really, I guess thinking about it, Mars is probably the best place then in terms of where it is in the solar system and how big it is to be this depository of meteorites.
Yeah, well, Shoemaker, which was one of the, I guess you could say, founding fathers of planetary geology, he calculated that the amount of material falling to Mars is roughly about 2.8 times more than what falls to Earth. And there's a few things going for Mars. It's smaller, so its entry velocity's tinier, but because it's got a thinner atmosphere, they end up hitting harder. But that might not necessarily be the case billions of years ago when it still had a thicker atmosphere to hold on to water. So, and the lifetime of a meteorite on Mars can last potentially billions of years. And from looking at meteorites on the surface using the rovers, they looked at meteorites, that Opportunity looked at meteorites, and it managed to calculate that the Amazonian weathering rate. And if you extrapolated it along the curve, these meteorites could have dated back as far back as a Hesperian transition when everything was starting to dry out. There was still liquid bodies of water. So these meteorites could have been on Mars potentially when there was still active life, which is really, really interesting. So because they can last for billions of years, these are essentially a witness plate for the vast majority of the planet's history.
So with that in mind, you say that these meteorites can last on the surface for billions of years, and therefore they can record these signatures of life from the past. But how long can life live inside of a meteorite?
Who knows? Yeah. Who knows? The way I try and see these meteorites is more as a lifeboat. So they're not actually a place that you'd really want to live. It's like, the ship sinking, you get into a lifeboat, but you wouldn't want to raise a family and 3 kids in there, right? Like there's a limited amount of resources, there's a limited amount of time you can actually stay in a lifeboat. And I think that's probably what was happening to these meteorites. We go to places on Mars, the site selections we go are really gravitational lows because that's where sediments come in, that's where clays come in. They're gravitational lows, we know that's where water accumulates, right? But it's also a place where there was probably stable bodies of water and lakes, but it's also where meteorites land. And we know that's not necessarily out of the blue because we go to Gale Crater, which was a gravitational low. We know there's a lake there, and we find meteorites. So, and what's really interesting, we find that these meteorites are not a strewn field. They're different meteorite types, which is really, really cool. That's a new finding by the ChemCam crew. So it's potential that some of these meteorites may have been just fell in an old Martian lake. They were buried in settlement, and then as the Mars dried out, and then you've had these sort of Aeolian presences eroded away. They've been exhumed again. So essentially what these things could have been is that these were, and because they would have used up a lot of the redox materials in the lake and everything, these meteorites would have been probably one of the last redox gradients at the surface of Mars, which could have been used by microorganisms to live. Obviously, not forever, And if you're weathering a meteorite, you want it to stick around, so they clearly didn't have much of an opportunity to be there. But it was definitely one of the last redox gradients at the surface of Mars.
So I guess in theory, so you're looking for these biosignatures then. So hypothetically, if you found one in a Martian meteorite, how much information can you then extract about what type of organism lived there, or is it just a case of life versus no life?
For instance, we know that on Earth there's different types of microorganisms, and there's some types of microorganisms that like eating organic material, with the heterotrophs, that's like you and me, and then there's chemotrophs, right, which are ones which live off the sort of metals and the sulfurs and stuff like that. I'm interested in sulfur sort of metabolisms because meteorites are full of sulfur, and because we've been studying them, we know what the value should be. It's 0, like 0 Canyon Diablo Troilite, like for the isotopes. So if we find that we get this material back and it has been biologically shifted in D34S, we could say that potentially that these things have been metabolized by a sulfur metabolizing organism. So that could give you some idea about its lifestyle. But beyond that, it would be pretty difficult to try and determine something else.
Is it unlikely to find paleofossil remains of these kind of organisms?
Well, no, it's interesting because inside a meteorite, because there's so many different types of minerals inside a meteorite, when they weather and break down, you really get sort of like a preservation trinity. You get your clays and smectites, which are really good for holding onto organics. You have your sulfates and iron oxides, which are, moderate. They're not the best for preserving fossils, but they can, and they've been known. And you also get carbonates as well. And all these ones can also do potentially isotopes as well. And there's by looking at preservation of microbiology on places on Earth, we know that we can rank these sort of minerals in a way of how good they are preserving organics, fossils, or isotopes, right? They're the three sort of things that you want to try and find for a biosignature. Or obviously organics are the best, because if you find, a DNA backbone and some nucleotides, collect your Nobel Prize. But, the other thing is isotopes are pretty good, but fossils themselves, although look really good in sort of scientific papers, are not the best way of determining a biofossil, because there's so many abiotic things that can look biological.
Right. And I guess that brings us to the famous example, doesn't it, of the Allan Hills meteorite?
Yeah, the ALH 84001, the rock that launched 1,000 careers, and arguments.
So sorry, what happened with Allan?
So this was, when was this? In the 90s,
96.
I guess? 96, yeah. There was a very famous paper published arguing that they'd found trace fossils in this Martian meteorite that turned out to be... well, not at all.
Yeah, so there was it's a very interesting sample. It's also as interesting as the politics behind it. There was a lot of it was at JSC. There was a group of people who kind of kept it from other people at JSC, like this is ours. Yeah. And that kind of stepped on a lot of people's toes, because it brought the whole world's attention to JSC, and that annoyed a bunch of people. Even the president at the time, Bill Clinton, got in and said, "We found life." They made this massive press release and everything, and they showed this beautiful thing that looks like a slug, essentially. But the problem was it's way too small. We're talking between 20 and 200 nanometers for a microbe. Now, the smallest microbe on Earth is about 0.3 micron, 0.4 micron. So, and the things that they'll point. So we're talking about stuff which is only around about the thickness of a cell wall. So there's but it got the scientific community asking, well, what is a biosignature, right? Because they made all these claims about why it was a thing. The first one is it looked like a bacteria, which is not very good. The second one was we had these polyaromatic hydrocarbons, so like organics, and they were trying to say that those organics would have come from meteorites on Mars, funnily enough, like contamination. It could also just been contamination from the Antarctic ice. We really don't know. Then they were looking at the isotopes in that stuff and said it's got a much higher isotopic range than Earth, so therefore life. But the trick is we don't really know much about the isotopic range on Mars, so that's not really a good answer. So there was all these things, and the last one was they had these tiny little magnetic crystals, which kind of looked, they said, microbes can make these as well, but the thing is, so can heat and pressure, such as an impact, like that probably ejected it from Mars in the first place, right? So there's a lot of arguments there that were circumstantial, but together they didn't really stack up. But the one that was the most easiest to disprove was the fact that they look like bacteria.
Yeah.
So the funny thing is that when you put a sample in an electron microscope, you need to coat it in a small, very thin film of metal to conduct all the sort of electrons away. Otherwise, you get this thing called charging and you can't get photos. One person found out that if you put just a little bit too thick of a gold coat on it, you get these tiny little bacteria-looking shapes and everything at the same size. Yeah. So it was pretty much shown that these were actually just a thick gold coat.
God. Wow.
But as contentious as it was really really important for two things, because it kick-started the field of astrobiology. It took it out of essentially the fringe and brought it into the thing now. And now we have
into the mainstream.
Yeah, so now we have journals, we have conferences, and we have the NASA astrobiological postdoc program. But what also at the same time was it also helped get funded the rovers Opportunity and Spirit, as well as the orbiters that went around at that time as well, because all of a sudden you had community interest in America and a public interest about kickstarting that. So in some respects, and it was a very important find just for that in itself.
So it's unlikely that obviously Allan Hills had any life in it, but a word you taught me today in your talk was panspermia. And that is when life is moved by a meteorite essentially to another planetary body. And I assume you probably have heard theories, though, that Mars is where life may have started, and panspermia brought it to Earth.
We're the Martians, we're the aliens,
that we are all actually Martians,
Well, that was really interesting. The research around panspermia was, when it was first proposed, everyone was like, that's ridiculous, that'll never happen. And what these scientists did in the 80s, the late 80s, so they got a piece of basalt, they dipped it in some microbes, and they put it into one of the NASA guns, which is designed to go at orbital velocities, killed 99% of bacteria, but not all, and they managed to culture from the stuff that some bacteria survive. So it went from, that's a joke, that'll never happen, to, of course. So almost overnight. And the Russians did something which was way, way cool. Is they on a satellite, they got I don't know how they got approval to do this, but on a return thing from a base station or something like that, on the heat shield of coming back through Earth, they got some basalt which they inoculated with microbes and just put it in the heat shield, and it came down and landed, and then once again, they got it out. Yeah, sure, most things died, but then they got it out and cultured, and they still managed to get the trace organisms. Wow. And you see this heat shield, and it's molten. There's molten basalt and everything, but they still managed to get some microbes out there. So they managed to survive that. So really cool, crazy science. So we've solved essentially 3 problems with panspermia, which is getting it off the planet, which is shock. 2, re-entry, and 3, survival in deep space, because these things just essentially shut down and turn themselves into whatever.
Why do people think it came from Mars to Earth, though, specifically? Is that because Mars was habitable before the Earth really got into the relevant conditions for life?
To be honest, I can't really say, and it goes back to the stage we don't really know that much about early Mars, but it could be both. I mean, we could have sent stuff to Mars, or Mars could send back to us. We know there was water on both bodies at the same time. We know that there was a thick atmosphere both at the same time. And we know that there was enough material at the same time. Because
of orbits, it's probably easier then to get material from Mars to the Earth than it would be, say, from Venus.
Yeah, to be honest, that's a very good point, actually. It's much easier to get things into the inner solar system than from things in the inner solar system to out. So, actually, to be honest, that's probably the main reason, is the fact that it's much easier to get stuff from Mars to Earth than Earth to Mars.
But at the same time, there's no necessity for it if water was on both of them at the same time. But it's life is one of these things that if it gets started, it's very hard to get rid of. So believe me, we've tried.
Very, very hard to get off. So why life on Mars hasn't developed essentially is a very interesting question. That's why I know a lot of scientists think it's probably deep underground in aquifers, if it's still around. But if it's not there, then wow, that's an interesting thing. It's because we know there's a lot of material that's been throughout Earth's history shared between these 2 bodies. So why didn't anything get started, I think, is an interesting question, especially if you go back to 3.8 billion years during the late heavy bombardment, when there was a lot of material being shared. I read a paper once that showed that something like 1.5 kilos of material from the Chicxulub dinosaur impact would have made it as far out as Jupiter and to the moon. So 1.5 kilos.
Wow.
You know, or out that far.
Yeah.
You know, that could be carrying anything, right? You know, crash into Europa, Bob's your uncle.
You got
Fish swimming around.
London,
Yeah.
yeah.
Velociraptors.
Oh, I still love that. Has anyone seen the South Park episode of the whale on the moon?
Oh, yeah. Similar thing on Jupiter.
Man, I'd laugh so hard if we see like half a velociraptor on the moon. That would be the funniest thing.
So we've just got one last question that we've been asking everybody that comes on. Is there a particular part of science that's outside the sort of field of meteoritics or your own research interest that you find particularly interesting or fascinating?
Abiogenesis. So abiogenesis and organic research, essentially. So how do you go from essentially graphite to phospholipid, you know, DNA, RNA? How do you go? What are the steps involved to go from essentially, stardust through to squishy, smelly stuff?
Yeah, that is a fascinating thing, though, isn't it? I mean, I was watching some YouTube videos about people extracting DNA from.
That's how John does all his research.
No, there's a great channel out there where this Canadian guy does a load of chemistry in his garage, and he extracted a bunch of DNA out of strawberries. But it just sort of got me thinking how he was using these sort of very sort of non-biotic sort of processes to get to something that's biotic, and it's just fascinating.
Well, one thing I find very interesting about, say, the early Earth is that we've looked at the isotopes of, say, comets and asteroids and mantle degassing, and it looks like that our oceans about 50% mantle degassing water and stuff from essentially carbonaceous asteroids. It turns out that comets maybe not so much, but asteroids is where we get a lot of our water from. But if you look at, say, something like a Murchison meteorite, about I think it's like 2 weight% is its water, and then another 1.5 weight% of organics. Now, if you play that over, say, late heavy bombardment, that means 50% is water from Earth, another 50% is essentially water from asteroids. But then again, you could say that almost another 50% on top of that is organics. It would have been a smelly ocean, right? Like, it would have been just thick of just like complex, nasty smelling stuff, and then you would have suffocated and died. But that's so it's, I think a lot of people, when they go back to those things, they don't realize how gooey these oceans probably would have been.
Yeah, because I guess it would have been, I seem to remember in undergrad people talking about how it had been quite sort of fizzy as well, I guess, and almost like a sort of a Coke-like soup consistency, I suppose. Well, thank you very much for coming on. That was an absolutely fascinating talk. And are there any papers or any research you wanna plug at the end here? We can also stick links in the description.
I've recently got a couple of papers out on this. So I look at how the genetics of the populations of microbes which live on meteorites in the desert. We found that there's different microbes that live in the meteorite than live in the soils, which is pretty cool. So these have diverged the populations. I've also got another paper out there which looks at meteorites in the desert as a habitat in its own right. So looking at like how these minerals absorb water vapor from the desert at night and how it keeps microbes alive and stuff like that. So,
Grand. Thank you very much.
Thank you very much.
Thank you.